Hello everyone. Today our topic for the presentation is security at the transport layer using SSL and TLS. Our group members are Rohit Paswan, Abhay Pratap, Abhilash Biswas, Abhinav Byrisetty, myself, and Abhishek Giri. The transport layer security is a way to secure information as it is carried over the internet. Various examples are users browsing websites, emailing, instant messaging, and conversing via voice over IP. The next slide. The secure socket layer. The secure socket layer provides security to the data that is transferred between a web browser and a server. This SSL encrypts the link between the web server and the browser, thus making all the contents between them encrypted such that they remain private and free from attack. Secure socket layer is the most used internet security cryptographic protocol before the TLS was released. However, now the TLS has adopted the SSL protocol. The SSL architecture. This SSL is specific to TCP and it does not work with the UDP. The SSL provides application programming interface to applications. Many languages like C and Java use SSL libraries and classes are readily available. The SSL protocol is designed to interwork between application and transport layer as shown in the following image. Now over to Rohit.
Hello, my name is Rohit Paswan. My roll number is 18118062 from group number 1. SSL architecture itself is not a single layer protocol as depicted in the image. In fact, it is a composed of two sublayers. First, lower sublayer, it comprises of the one component of SSL protocol called as SSL record protocol. Second, upper sublayer, it comprises of three SSL related protocol components and application protocol. Application component provide the information transport service between client-server interaction. Next slide. The three SSL related protocol components are SSL Handshake Protocol, second change Cipher Spec Protocol, third Alert Protocol. Next, Record Protocol. Record Protocol to service to SSL connection. First, confidently. Second, message integrity. In the SSL record protocol, application data is divided into fragments. The fragment is compressed and the encrypted MAC message authentication code generated by the algorithm like SHA secure hash protocol and MD5 message digest is appended. After that, encryption of the data is done and in the last SSL header is appended. Next. Handshake protocol. Handshake protocol is used to establish sessions. This protocol allows the client and server to authenticate each other by sending a series of messages to each other. Phase 1. In phase 1, both client and server send hello packet to each other. In the IP sessions, ciphershoot and protocol version are exchanged for security purpose. Phase 2. Server send is certificate and server key exchange. The server and phase 2 sending the server hello and packet. Phase 3. In the phase client reply to the server by sending in certificate and client exchange key. Phase 4. In phase 4 change cipher shoot and occurred and after it handshake protocol ends. Next. Change cipher protocol. This protocol use the SSL record protocol. Unless handshake protocol is completed, the SSL record output will be in pending state. This protocol purpose is to pause the pending state to the copied into current state. Next. Alert protocol. This protocol is used to convey SSL related alert to the peer entity. Each message in this protocol contains 2 bytes. Level 1 and alert. This level is further classified into two parts. Warning. This alert has no impact on the connection between sender and receiver. Fatal error. This alert breaks the connection between sender and receiver.
Now the next part will be explained by Abhay Pratap. So over to you, Abhay.
Hello, thank you, Abhilash. My name is Abhay Pratap, roll number 181180001, and my topic is SSL message format. As Rohit said, that there are four type of protocol, there are four type of SSL message formats also. That is first one, record protocol general header. There are three length of type. First protocol, their length is 8 bit, and second is version, its length is 16 bit, and third one is length. Its length is also 8 bits. And the second one is change cyberspec message. It's same as the record protocol generator, but only one was added, CSS1. Their length is 8 bit also. Second slide. And third one is alert message format, and same as previous one, only two are added, label and description, and both lengths are 8 bit. And fourth one is Handshake Protocol message. In their version of headed type and length. There are type of 8 bit and length of 16 bit. Next slide, please. And a different type of handshake message. The follow as their different type of message invited by the handshake protocol as shown as in image. Next slide. Transport layer security (TLS). Transport layer security or TLS is a widely adopted security protocol designed to facilitate privacy data security for communication over the internet. And TLS was posed by Internet Engineering Task Force (ITTF), an international standard organization. And the first version of protocol was published in 1999. TLS evolved from a previous encryption protocol called Secure Subnet Layer, which was developed by Netscape TLS version 1.0. Actually belong to develop as a SSL version 3.1. Also, TLS does not support Fortanja method, which is an information security system that uses Fortanja crypto card and the PC-based security token developed by the US government. Next slide.
Thank you, Abhay. Now, the next part will be explained by Abhishek Kumar. So, over to you, Abhishek.
Uh, I'm Abhishek Kumar, roll number 191180004. So in this slide, we'll look at working of TLS. And basically for TLS to work, you have to get the TLS certificate on the origin server. And the certificate contains the server's public key and other details of who owns the domain. Now, we'll look at TLS Handshake. TLS Handshake has basically 4 parts: TLS version and the cipher roots, and then they authenticate the identity of the server using the server's TLS certificate, and for generating session keys. Next slide. So the TLS handshake establishes a cipher suite for each communication session, and the cipher suites are as below. So the general rule is TLS followed by key exchange followed by word with, then the encryption, and then the hash. Next slide. The handshake also handles authentication in the TLS, and basically this is done using public key cryptography, and the server public key is part of its TLS certificate. Next slide. And this we see how the client and server communicate in the TLS handshake. First there is a SYN message, and then the SYN is acknowledged, and this goes back and forth with the exchange of the hello message as well as the server's sides of verification of the client and the client side verification of the server. Now for the next slides, we'll go to Abhay.
My name is Abhay Pratap. My roll number is 191180001. Alert protocol in TLS. TLS supports all protocol defined in SSL except for no certificate, as shown in the image. And next slide. Handshake protocol in TLS. Handshake protocol I defined as shown in the image. There is types, and there are 2 types are handshake message MDH and SH1, and there is type of MDH5 also, and there are type of SSL1 also, and there are both are with hash and hash. And next slide, please. Record protocol for TLS. Record protocol TLS as shown in the image, like max secret left should bit size is 512 bits, and the total shown in the image. Second slide. Benefits of TLS and SSL. Over to you, Abhilash. This part of Abhilash.
Thank you, Abhay. I am Abhilash Biswas, roll number 191180002 from group number 1. So, benefits of TLS and SSL. First benefit of TLS and SSL is encryption. It can help to secure transmitted data using encryption. Interoperability. It works with most web browsers, including Microsoft Internet Explorer, and on most operating systems and web servers. Algorithm flexibility. It also provides operations for authentication mechanism, encryption algorithms, and hashing algorithm that are used during the secure session. Ease of deployment. Many applications, TLS and SSL temporarily on a Windows Server 2003 operating system. And lastly, ease of use. Because we implement TLS SSL beneath the application layer, most of its operations are completely invisible to the client. Now, coming to our model, we have made a model on OpenSSL. So, what is OpenSSL? It is basically a software library for applications that secure communications over computer networks against eavesdropping or need to identify the part at the other end. OpenSSL contains an open source implementation of the SSL and TLS protocols. The core library, written in the programming language, implements basic cryptographic functions and provides various utility functions. Coming to the usages of OpenSSL, OpenSSL is a cryptographic toolkit implementing the secure socket layer and transport-less security network protocols and related cryptography standards required by them. It is a command line program for using the various cryptography functions of OpenSSL's crypto library from the shell. It can be used for creation and management of private keys, public keys, and parameters, as well as public key cryptographic operations, creation of X509 certificates, CSRs, and CRLs, calculation of message digests and message authentication codes, encryption and decryption with ciphers, SSL TLS client and server tests, handling of SMIME signed and encrypted mail, timestamp requests, generation and verification. In this model, we have shown you the encryption and decryption as well as the signing of certificates, self-signed as well as the certificate authority signed certificates using OpenSSL. Further parts will be explained by Abhinav Byrisetty. So over to you, Abhinav.
I'm Abhinav Byrisetty, role 19118-003. Encryption and decryption. SSL and TLS uses both asymmetric and symmetric encryption to protect the confidentiality and integrity of the data in transit. Asymmetric encryption is used to establish a secure session between the client and the server, whereas asymmetric encryption is just used to exchange the data within the secured session. SSL and TLS encryption is great for security because it increases confidentiality and integrity. However, as attackers also use encryption to hide malicious payloads, effective SSL and TLS decryption is necessary for inspection tools. Here, we use the advanced standard encryption algorithm for encryption and decryption purposes. Since the AES algorithm is considered secure, it is in the worldwide standard. Next slide. The advanced encryption standard. The AES algorithm is a symmetrical block cipher algorithm that takes plain text in blocks of 128 bits and converts them into ciphertext using keys of 128, 192, and 256. The working of this cipher is AES performs operations on bytes of data rather than in bits. Since the block size is 128 bits, the cipher processes 128 bits of the input data at a time. Then a creation of round keys is done. A key schedule algorithm is used to calculate all the round keys from the key. So the initial key is used to create many different round keys, which will be used in corresponding round of the encryption. The next slide. This is a block diagram of how the AES algorithm works. The next slide. There are various modes in the AES algorithm, basically 5 modes of operation, which are namely the ECB mode, the electronic codebook mode, the CBC mode, cipher block chaining mode, the CFB mode, cipher feedback mode, OFB mode, output feedback mode, CTR mode, counter mode. Each mode of operation has its own parameters, which are important to provide the necessary security of the algorithm. The modes of the operation are the most important for a proper AES implementation. An improper implementation or use of modes of operation may seriously compromise the AES algorithm reliability. Next, we have the implementation part where we use the OpenSSL software where we encrypt and decrypt file using a RSA generated key pair. We share the public key among two different users and use it to encrypt files and then decrypt it using the private keys of the each. Before that, we show an implementation of simple encryption and decryption algorithm of how it's done using the AES algorithm. The next slide. These are the few screenshots of how the implementation is done. The next slide. This is where we generate the key pair. Next. Next. Here it shows the private key of both the users. Next. Then we generate the public key using the command line commands. The next. Here we generate a text file and copy it from one user to other user, encrypt and decrypt it using the key pairs. This is how the encryption and decryption is done in AES.
Thank you, Abhinav. I am Abhilash Biswas, roll number 19118002, and now we are going to see how to make self-signed certificates using the OpenSSL library. So a self-signed certificate is one that is neither private nor public and is not signed by a CA. Instead of obtaining a certificate from a public or private CA, the certificate is signed with its own private key. In this situation, the certificates we shall be creating and signing will follow the X509 format. A digital certificate based on the widely acknowledged International Telecommunications Union (ITU) X509 standard, which defines the format of public key infrastructure (PKI) certificates, is known as an X509 certificate. They are used in internet communications and computer networking to handle identity and security. They are unobtrusive and everywhere, and we see them all the time when we use websites, mobile apps, online documents, and linked gadgets. Moving on to the implementation part, first of all, we will start by making a private key. The most significant component of our certificate is the private key, which aids in the encryption. As we can see, the following is the command for creating an RSA key, private key. After that, we will uh, create a certificate signing request, which is required if we want our certificate signed. The public key is included in the CSR, as well as some additional information such as organization and country. Let's make a CSR from our existing private key. And as you can see in the output, the following is the command. After that, a self-signed certificate is one that is signed with the certificate's own private key. It can encrypt data just as well as CA signed certificates, but it will display a notice that the certificate isn't trusted to our users. With our existing private key and CSR, let's make a self-signed certificate. So as you can see in the final output, we see that the signature is okay. So the signing is successful. After that, by creating a self-signed root CA certificate and then installing it as a trusted certificate in the local browser, we can be our own certificate authority using the following commands. After that, with our root CS certificate and associated private key, we can sign finally our CSR. And finally, to read the contents of our certificate in plain text, we may use the OpenSSL command, and the output will look as follows. This was all about our presentation. We will now be we will be explaining further in the demo of this presentation. Lastly, we have the conclusion. So we have thus shown the encryption and decryption algorithms using OpenSSL and also shown how to create a self-signed certificate with OpenSSL from scratch. View the certificate. In previous sections, we discussed SSL and TLS in detail and saw how TLS has evolved from SSL into a more modified and better performing algorithm. We also briefly discussed the other versions of SSL like Boring, Lieber, etc. After going through our research, we have found the following benefits of SSL and TLS. SSL TLS uh, can aid secure data transmission by encrypting it. Most web browsers, including Microsoft Internet Explorer, as well as most operating systems and web browsers, support TLS SSL. And as follows. Now we will move on to the demo part of our presentation. First of all, it will be explained by Abhinav Byrisetty. He will be explaining and showing us the encryption and decryption aspects of OpenSSL, followed by me, Abhilash Biswas, who will further explain the certificate signing requests using OpenSSL. Thank you, guys.
Hello, I'm Abhinav Byrisetty, role 1911800. I'll be showing a sample based on encryption and decryption using OpenSSL. Initially, we create a sample text file with a message in it. command displays the contents in the file. Now, we try to encrypt it using various OpenSSL commands. The, the OpenSSL has a various type of commands, encryption algorithms and modes, the AES algorithm, the ARIA algorithm. I'm choosing the AES, the Advanced Encryption Standard algorithm, with the electronic control block mode, which has 256 bits. The command for the encryption goes like OpenSSL. ANC indicates encryption. We use the AES 256 ECV mode. The PVKDF2 command is a password-based key derivation function. It derives key from a password using a salt and iteration count. The iteration count is then set to 1 lakh. The salt command. This is being used when the first 8 bytes of the encrypted data are reserved for the salt. It is generated at random when encrypting a file and read from the encrypted file when it is decrypted. Without the salt option, it is possible to perform efficient dictionary attacks on the password and to attack stream cipher encrypted data. The reason for this is that without the salt, the same password always generates the same encrypted key. This then takes the input as the sample text file we just created and outputs in cipher.txt file which has the encrypted key. The password is used to protect the file from others while attempting to decrypt the file without the password. Now we can see the sample text file is encrypted in this. This, this shows the encrypted data. Now we try to delete the sample text file. So we don't have any sample text file now. We bring it up by decrypting the encrypted text file. The command then goes like OpenSSL. The D stands for decryption. We again use the AES algorithm with the ECB mode. The PDKDF2 command. The iteration count set to 1 lakh. Salt command. Here we input the cipher.txt as input and we output a sample.txt file. The password is the previous password which we used to encrypt it, and this out creates a sample.txt file which has the original contents as you can see. Now we will see the encryption and decryption among two users, Alice and Bob, who want to communicate with each other by exchanging encrypted files using OpenSSL. For this, we create two different directories, A and B, so that it seems like we're working with two different systems. Before we can encrypt files, we need to generate a pair of keys. The command for this goes like OpenSSL genRSA, which generates an RSA key pair, outputs in the file keypair.pem, contains 1024 bits. This command uses OpenSSL's genRSA command to generate a 1024-bit public and private key pair. This is possible because the RSA algorithm is asymmetric. The contents of the key pair in the PEM file are. This is the private key generated from key pair A file. Similarly, we generate the key pair with Bob. OpenSSL genRSA outputs a key pair B.pem file. As you can see, we generated two different key pairs, one for Alice and one for Bob. To view the case details, you can use the following OpenSSL command to input the .pem file and display the contents. This outputs in the form of text. This is a private key, contains 1024 bits, modulus, a private exponent, two different primes, two exponents, quotient, and the private key which you have seen earlier. Okay, PM output. This is the similar one we have seen with Alice. Then we extract the public keys from this key pair. For that, the command we use is OpenSSL RSA. We input the key pair file, output public key.pem file. This displays the contents of the public key we generated. Similarly with Bob. These are the contents of the public key of Bob. Since we have the public keys with each Alice and Bob, we need to exchange them among the users. These public keys are not much used to Alice and Bob until they exchange them with each other. Several methods are available for sharing public keys. A simpler way is to copy the keys to each other directories. As you can see, the files are copied to each other directories. Now Alice has Bob's public key and vice versa. Then we exchange encrypted messages with the public key. Alice communicates with Bob through a message in a text file. We need a text file. You can see a sample a.txt file is being created. The contents of the file are this is a sample text from Alice. To encrypt this message, Alice needs to use the OpenSSL encrypt command. She needs to provide three inputs to the tool: the name of the file that contains the message, Bob's public key, the name of the file where the encrypted message will be stored. The command goes like OpenSSL tkutil encrypt. We input the sample text file we just created and output the cipher.exe file uses the key Bob's public key. You can see the file is encrypted. The contents of the encrypted file are as you can see the contents of the encrypted file are not the original contents which you have written to the text file. The tkyult command is used to perform low-level public key operations using any supported algorithms. Since we have encrypted the text file we generated, next it's safe to delete the original file with the message to remove any traces of it. Since the file is deleted, now Alice needs to send this encrypted file to Bob over a network. Here, we copy the file to the other directory. Even if the file is intercepted in between, its contents are encrypted, so the contents cannot be revealed. Now we can see that one file is copied to this directory, and if we try to view the contents of the file, they all are encrypted. So we cannot use usual methods to view the message. Hence, we need to decrypt the file using the OpenSSL by using the command decrypt. He needs to provide the following information to the utility: the encrypted file which he got from Alice, Bob's own private key, a file named to save the decrypted output to a redirection. The command goes like OpenSSL PYUTL decrypt The input key we give is the private key we generated in the beginning. We input the cipher file we receive from A, which outputs a sample text file. We can see the contents from the text file after decryption are same as before the encryption near Alice, even though the file contents are deleted. Repeat the process with the other key for the opposite communication. That's how the encryption and decryption are done using the RSA key pair. Thank you.
Hello and welcome to our demo of the OpenSSL library. I'm Abhilash Biswas, roll number 19118002, Information Technology 6th semester and from Group 1. And today I'm going to show you guys a demo of signing certificates with OpenSSL certificates. So certificates are basically a part of a subfield of cryptography called asymmetric key cryptography. And the basic idea is that you have a public key and a private key. The public key is what is exposed to the world and is used by other people, entities, computers to communicate with you. And the private key is what you have to either verify what they have sent you or encrypt things that you are sending to them. So without further ado, let's get into our demo. So first of all, let me show you what OpenSSL is. So let me hit the OpenSSL command. Now I'll type help to see a list of bunch of commands that the OpenSSL library has for us. Now we will start with our demo. So first of all, we'll do a self-signed certificate. And for self-signed certificates, I have two methods. One is a very long method and one is a method which is quite short and consists of only one line command. Now let's start by making a directory in our desktop. So I'll change my directory to desktop. Okay, cd desktop. Now I'll make a directory by the name of OpenSSL. There we go. Now I'll change my directory to OpenSSL. Right now I am in the OpenSSL directory. Now let's start by creating a key for our certificate. So for that, I'll put OpenSSL, then generate an RSA key. The output should be saved in a file called ca.key and with 4096 bits. As we can see, it has been created. In order to confirm that, we will do ls and check. So we have our ca.key with us. Now we will create a certificate signing request and immediately sign it. How we are going to do that? Let me show you. So I'll type OpenSSL request, signing request, X509, which is nothing but the format of the certificate which we are going to create, and the key that we are going to use is ca.key that we created earlier, and the output will be ca.certificate. And let me say that this certificate is valid for 365 days. Now I'll hit enter. All right. So now it will ask me for a bunch of information that we are going to fill. First of all, it's asking me a country's name. So I'll say India. Then state or province name, I'll put Chhattisgarh. For locality name, I'll put Raipur. For organization name, let me put NIT. And for unit name, let me put IT. For common name, let me put my common name here and my email address, which is as follows. Now it has been created. Now let's see if it's in our directory. I'll put ls and see that the certificate has been created as well as the key is there. All right. Now let's view the contents of our certificate that we just created. So I'll do vica.crt. As you can see, this is my certificate that I have generated, and this is how it will look like. Now let's create. Now that it has been created, let me do another command and just show you the contents of the certificate along with the information that we just filled. We are going to do that by pressing the following commands. We will put no output so that we separate output isn't created for us. However, we do need to see the text. So we will type the text command, and then the input we are going to take is ca.certificate since we want the contents of the certificate. I'll put enter, and now as you can see, these information that I filled, my country, state, my organization name, email address, etc. And it will also tell me for how long the certificate is valid. So exactly an year from now. And this is again the base 64 encoded data. And we are using the AES algorithm for it. So basically, this certificate is not trusted since it is in PEM format or PEM format, but it will be trusted when imported using the PKCS12 or PFX format, which is valid for Windows. Now moving on, like I said earlier, we can either do all of this using several lines of code, or we can do it in one single line of code. Let me show you the second method, which is the shortest method for it. Now I will type out the following command. So OpenSSL signing request. I'll create a signing request of the format 509. I'll say new key. That the new key that I'm going to create, which it will also follow the RSA algorithm, 4096 bits again, and the key out, the output. Let's say it's not CA dot key, and the output is not CA dot cert. All right, and the days will be 365. Of course, it's valid for a year, and I'll put nodes, and then I'll hit enter. As you can see, it has been created again, and again it is asking me for the information. So let me fill random information. Say Raipur. Organization name, let's put NITRR this time. And the organizational unit name, again, let's say IT. Common name, let's say Abhilash. Email address, I'll put the same email address that I used earlier. Now, in order to view whether this has been created properly, let me put ls. So we have the not ca.cert as well as not ca.key in my directory, and whether my certificate was created properly or not, I will in order to view the contents of the certificate, I'll use that command again. So OpenSSL x509 no out, since I don't want an output with me, text, and for this time the input is not ca.cert. C, and yes, it is the process is complete. We have our issuer, the information about the issuer, which is the country, state, and Raipur, organization, email address, etc. The time that it will be valid for, as well as our base 64 encoded data using the RSA public key. Right. So the self-signing certificates are done. Another thing that can be done using OpenSSL is that we can use a certificate to sign another certificate. Now this is an interesting one. How we will do it is as follows. Now, first of all, I'll do OpenSSL and generate an RSA key again. Let me call this RSA key as securable.key. Now I am using the second method this time for signing the first certificate so that we can wrap it up a little faster. Okay, so securable.key, and then I'll create a 4096 bit securable key. All right. Okay, it's done. Then OpenSSL. We will create the certificate signing request now. So OpenSSL request new key, and our key is securable.key that we created a command ago. And I'll save my output in securable.csr, which is nothing but the certificate signing request. Now let's fill the form again, and our information will be stored. So let me do it again. INCG, locality name, let this be Raipur. Organization name, let this be NIT Raipur again. Organizational unit name, let me put IT1 this time. And common name, Abhilash. Email address will be the same. Now it will ask me for a password. So yeah, let's put password as just password for now. An optional company name, let me put, say, NITRR 1. So it is complete. Now let's sign the certificate that we just created right now. For that, we will use the following command. Now remember, keep in mind that we are using a certificate to sign the certificate, and a while ago I created a certificate by the name of ca.crt and ca.key, so we will be using those certificates to sign this certificate. So let's see, OpenSSL x509, which is my format again, creating a request. The input is securable.csr and CA, certificate authority, is ca.cert. Certificate authority key is ca.key, and of course creating a serial, which is important because we need a unique serial number for our certificate. For that we will be using this command, and output will be stored in a file, let's say securable.cert, and let this be available for a year, so 365 days. Now I'll hit enter. Now as we can see, the information is there and the signature is okay. So it's successful. Now finally, in order to view the contents of this certificate that I put, we will use the command again, OpenSSL X509, no output since we do not require an output, and only the text. The input will be securable.crt. As we can see, the signature algorithm this time was SHA 256 with RSA encryption, and the information again is as follows. As you can see, my information. This is the modulus, which is again the base 64 encoded data. And of course, the signature algorithm was SHA 256 with RSA encryption. So that's it from my side, guys. Thanks a lot.